I thank the witnesses all for your testimony, and I now recognize myself for 5 minutes for some questions. And back with you, Dr. Jansen, I particularly zeroed in on your testimony about AI. This committee kind of ran point last year when we did the AI task force. The Science, Space, and Technology Committee was kind of the core of that group, even though it crossed all disciplines across Capitol Hill here. Growth in AI, as we know, it's exponential, it's ubiquitous, it's now on the tip of everyone's tongue and everywhere we go now. And we have to continue to lead. I appreciate what you said, we're either going to lead or we're going to follow. With respect to Bristlemouth, can you tell me a little bit more about that and how it's driving the cutting-edge data assimilation techniques? The decision to go open source. We debated that a lot in our task force last year. There's pros and cons, but in the case of what you guys have done with Bristlemouth, can you talk a little bit about that decision?
Yeah, I can. First off, I think it's really important to see sort of like the state of where we're at. This is still very, very nascent in terms of like technology development in the ocean. As a result, I think one of the most important things is that we should not think in zero sums. The sum is small. We should increase the sum. And so with Bristlemouth, and this is part of like, if you think about AI, we need to get to abundant data one way or the other, right? Without that, AI cannot exist. We used to have models that could understand physics because we put the physics in there and then we just need data to start them. Now we need basically data to teach these models what physics looks like. So we need a lot more data than we ever did before, but the opportunity is massive. Now, if you think about where it starts, is sensing. And so today, the state of the art in sort of like marine sensing technology is roughly equivalent to you getting handed a mouse with bare wires, and you're going to have to figure out how to make that work with your computer. Pre-USB desktop computing. Even if a plug looks like it fits the other one, if you put them together, usually one of the sides starts to smoke, and certainly nothing is going to work. And so that's where the first hurdle starts. To scale sensing, we need to make interconnectivity of hardware much simpler, just like we did with USB, with incredible outcomes. And so Bristlemouth is exactly that. The decision to open source was not free. Like, as a company, we would have not open sourced it because it's expensive and we could not justify the investment. It would have been valuable for us and we would have just done that. But by partnering up with the government and wanting to make it open source, because still the benefit to us would be equal, but the benefit to society and the ocean community would be massive, we decided to do that with support from philanthropy, the Office of Naval Research and NOAA. And so it is a decision that costs money. It's a decision that will have to be made sort of like carefully, but I think it's the right decision. The most important thing is that we get ourselves out of the hole and get to large-scale ocean sensing as quickly as possible.
Very good. All right. My hometown is Lakeland, Florida. We're home of NOAA's Aircraft Operations Center. We have the Hurricane Hunters. I had the privilege, along with Representative Frost, last year to go up in Hurricane Milton. At the time we flew into it, it was, I think, the 4th or 5th strongest storm in the Atlantic Basin on record. Exciting journey. My hat's off are to the men and women who fly those missions all the time. They provide very critical data that we need as these storms are evolving to keep our people safe. But they can only paint, the hurricane hunters only paint a part of the picture of these storms, and ocean data can unlock the true driving forces behind these storms. We're lacking real-time information to complement the aircraft data. For all of you, I'd love to get your thoughts on some of the operational technology you're either using or developing or seeing coming down the track that can assist NOAA in unlocking these driving forces behind these hurricanes. And Mr. Childress, if you want to start that one.
Sure. Probably on this panel, not the best guy to answer, but I think the bandwidth availability globally now means that we get data available quickly. Margaret was talking in the anteroom coming in about biogeochemical floats that are actually making analysis of genomes and then transmitting that data back all the time. We're seeing that in the commercial world with bandwidth availability all over the globe where we can remotely control USVs, ROVs, others without people in the field. So I think bandwidth development and availability is a key breakthrough for us.
Mr. Smith.
If I could answer it slightly differently, because one of the things we're interested in is the impacts of the storms as well. And we've done a lot of work in coastal mapping, both at Exocean, of course, at NOAA, on the storm run-up models for storm surge, and what project that Exocean did for NOAA a couple of years ago was exactly that in the coast of North Carolina for updating those storm surge models to be able to understand what the impact was of the storm.
Okay. Dr. Lynan?
Yes. So one of the critical elements for hurricanes is their intensity. And the intensity is related to the heat in the upper ocean. And the importance of that and the dominance of that was actually developed by a University of Rhode Island oceanography professor, Isaac Guinness. And the key there is that it's not just the temperature of the surface, which you can get from satellites, but you have to have the heat of the entire upper layer of the ocean, and that demands robotic capabilities. So that's a really important factor there. On the West Coast, we're more concerned with atmospheric rivers than hurricanes, and they cause a tremendous amount of damage. Those are an oceanic phenomenon, and in order to be able to predict them and to determine how strong they are, and they have a scale, a 5-point scale just like hurricanes do, you have to have the information from the ocean and the atmosphere interaction with it. And as you and I discussed, the hurricane flights during the non-hurricane season are out on the West Coast looking at atmospheric river recon. And not only is that important for the storms that hit exactly on the coast, but those atmospheric river systems go inland. They're lifted up by the mountains, and they're responsible for the huge snow events and the severe storms in the Rockies and in Colorado. In fact, the avalanches earlier this year were the direct result of an atmospheric river. So this ability to set up the observations that allow us to make these predictions for extreme weather events are critical. And I think the work by Dr. Guinness was taking place during the 80s and 90s. The work for atmospheric rivers is taking place now. And then that work eventually is handed off to the ability of the private sector to be able to do these kinds of measurements. And it's tremendous to be here and watch these companies, which have oceanographers working with them, take the results from that early research and turn it into products and services for all of us. And NOAA is the glue in the middle of that between the academic world and the private sector world.
Thanks, Dr. Lyon. Dr. James, I'm going to have to get back to you separately on that. Out of respect for my colleagues, I'd now like to turn it over to the ranking member from Rhode Island for 5 minutes of questions.